When we think of Mount Etna, we usually imagine a towering peak on the island of Sicily, crowned with fire and belching thick plumes of ash into the Mediterranean sky. It is Europe's most iconic and active volcano, a landmark that has shaped human history for millennia. But today, the world's leading geologists and volcanologists are turning their gaze away from the smoking craters at the summit. Instead, they are looking down, deep beneath the sapphire blue waters of the Ionian Sea. There, hidden from sight, lies a geological monster. It is a massive block of volcanic rock, an entire flank of the mountain, that is slowly but surely sliding into the abyss. This is not a story about an eruption of lava. It is a story about the relentless, silent power of gravity. It is the story of a 25 cubic kilometer mass of Earth that could, at any moment, trigger a tsunami capable of reshaping the coastlines of 3 continents. Section 1. The immense scale of instability. To understand the danger, we first have to grasp the sheer scale of what we are talking about. Scientists estimate that the unstable southeastern flank of Mount Etna covers a volume of roughly 25 cubic kilometers. To the average person, that number is hard to wrap the mind around. Imagine a slab of earth large enough to fill 10 million Olympic-sized swimming pools. Imagine a mass of rock so immense that if it were to crumble, it could bury the entire city of Catania under hundreds of meters of debris. This is not a theoretical fear. The seafloor around Sicily is a graveyard of past disasters. Deep-sea cores and seismic imaging have revealed layers of chaotic sediment, jumbled blocks of rock, and ancient mudflows that stretch for kilometers across the seabed. These are the silent witnesses to prehistoric collapses. The most terrifying record dates back roughly 8,000 years. Geological evidence suggests that a massive section of Etna's flank gave way back then, plunging into the sea with such violence that the resulting tsunami left its mark as far away as the African continental shelf. Today, scientists see the same patterns emerging. The mountain is shifting again, and history has a habit of repeating itself. Section 2. The force of gravity versus the power of magma. For decades, the scientific community operated under a specific assumption. They believed that the eastward movement of Etna's flank was driven by the pressure of rising magma. The logic was simple. As the volcano filled with molten rock, it expanded, pushing its sides outward. However, a paradigm shift occurred in recent years. New data from the seafloor have overturned this long-held theory. By analyzing deformation patterns, researchers discovered something startling. The movement is actually smallest at the summit and grows larger as you move toward the submerged edge. If magma were the primary engine, we would see the most movement near the vents at the top. Instead, the deepest parts of the mountain are moving the fastest. The culprit? Gravity. Mount Etna is built on steep slopes and sits atop weak, clay-rich layers of sediment. These layers act like a giant geological lubricant. Under the sheer weight of the volcano, the entire southeastern flank is being pulled downward by the Earth's gravity, sliding toward the deepest parts of the Ionian Sea. This was confirmed in a dramatic way in May 2017. A network of underwater sensors recorded a slow slip event where a section of the submarine fault moved more than 4 centimeters in just 8 days. Crucially, there was no eruption at the time. This proved once and for all that the flank can accelerate and move independently of the magma inside. While a new eruption can certainly act as a trigger by adding internal pressure, the primary driver is the mountain's own crushing weight. Section 3. The technological frontier, monitoring the abyss. How do you track a mountain that is moving underwater? It is one of the greatest technical challenges in modern science. Traditional tools like GPS and satellite radar are useless once you go below the waves, because water blocks the signals. To solve this, international teams have turned the seafloor into a high-tech underwater nervous system. At the heart of this system are acoustic transponders. Anchored at depths of over 1,200 meters, these devices act like underwater satellites. They send out high-frequency sound pings to one another, measuring the distance between points on the fault line with millimeter precision. When the 2017 slip occurred, it was these pings that alerted scientists that something was wrong. Alongside these, researchers have deployed pressure sensors. These instruments are so sensitive they can detect a minute change in the weight of the water column above them. If a block of rock begins to move or sink, the pressure changes, sending an instant signal. We also have fiber optic DAS, or distributed acoustic sensing. Scientists are now repurposing existing underwater telecommunication cables, using them as thousands of tiny vibration detectors. This allows them to hear the microquakes, the tiny snaps and groans of the Earth as the flank struggles against friction. Finally, GPS-equipped buoys float on the surface, acting as a bridge. They collect the data from the seafloor via sound waves and beam it up to satellites, relaying it in real time to monitoring centers in Rome and Catania. But there is a sobering reality to all this technology. These systems can tell us a collapse is happening, but they cannot predict exactly when the final breaking point will be reached. Section 4. The human and economic cost. The stakes of this research could not be higher. This isn't just a fascinating geological puzzle. It is a matter of survival for more than 3 million people. The eastern coast of Sicily is a vibrant, densely populated region. Cities like Catania and Syracuse are not just historical treasures, they are modern economic hubs. If the flank were to collapse, these cities sit directly in the impact zone. The local economy is deeply tied to the sea. Coastal resorts, marinas, and fishing fleets support thousands of families. Then there is the infrastructure, the vital highways, railways, and power lines that hug the narrow strip of land between the volcanic slopes and the water. The economic exposure is staggering, estimated in the tens of billions of euros. A collapse would do more than just destroy homes. It would sever the logistics links between Sicily and mainland Italy, potentially causing an economic crisis that would be felt across the entire Eurozone. Section 5. The 15-minute warning. The most chilling aspect of a submarine landslide is the timeline of the aftermath. When an earthquake happens in the middle of the ocean, it can take hours for a tsunami to reach distant shores, giving people time to react. But a landslide at Mount Etna is a local event. The physics are brutal. From the moment the flank begins its catastrophic slide to the moment the first massive wave hits the Sicilian shore, the window of time is estimated to be just 15 to 20 minutes. This is the tsunami window. In less time than it takes to have a cup of coffee, hundreds of thousands of people would need to move to higher ground. This leaves virtually zero margin for human error. Because the Ionian Sea is a shared space, the threat doesn't stop at Italy's borders. It is an international emergency. Agencies like UNESCO and the National Tsunami Warning Centers of Greece and Tunisia are now working together. They are trying to build a unified Mediterranean warning system that can bypass bureaucratic delays. The challenge is as much political as it is technical. How do you ensure that a warning triggered by an Italian sensor instantly activates sirens in a Greek village or a Tunisian port? They are conducting cross-border drills to find out, trying to eliminate the language lag and ensuring that evacuation routes in every country are clearly mapped and ready. Conclusion. Action before the unthinkable. Mount Etna's southeastern flank is a reminder of our planet's restless nature. We have learned that the mountain doesn't need to erupt to be dangerous. The shift from a magma-focused model to a gravity-driven model has changed everything. It has added a sense of urgency that didn't exist a decade ago. We now know the scale of the mass. We have the sensors in place to hear it moving. We know exactly how much time we have if the worst happens. But the gap between scientific detection and real-world readiness is still there. Preparedness isn't just about more sensors or better data. It is about building a culture of awareness. It is about hotel managers in Taormina, fishermen in Syracuse, and families in Catania knowing exactly where to go when the sirens sound. Nature operates on a timeline that we cannot control. The geological memory of the Mediterranean tells us that the flank has fallen before, and it will fall again. Our responsibility is to ensure that when that day comes, we are not just spectators to a disaster, but a society ready to save every life possible. The giant is moving. The question is, will we be ready when it finally lets go?